Hello everyone, my name is Seiji. I'm gonna talk about the acoustics of cross-fingering. I'm often asked why a pitch is bent due to cross-fingering. I hope this video will give you an answer. First of all, what is cross-fingering? It's a technique of playing woodwind instruments where one or more tone holes are closed just below the first open hole. If you play the instrument with cross-fingering, you usually get a pitch lower, a semitone or whole tone lower than that played with normal fingering. So this is a way to play accidentals or the pitches that are not on music scale on keyless woodwind instruments like recorders, Krumm horns, and shakuhachis. However, in exceptional cases, cross-fingering results in a pitch higher. This is called intonation anomaly. I will show a few examples on the recorder. The first three are in the lower register. You can play C5 with normal fingering. If you close two holes just below the first open hole, then you would get B4, which is a semitone lower. Similarly, you can play D5 to C sharp 5, E5 to E flat 5. In the higher register, you can play C6 with normal fingering together with the pinched thumb hole. If you close one hole this time, you would get B5, which is a semitone lower. Similarly, you can play D6 to C sharp 6. However, if you close two holes, then you would get E6, a whole tone higher. If three holes are closed, then you would get D sharp 6, a semitone higher. I began to play the recorder when I was a kid. Since then, I have known these pitch bending phenomena. However, it was very recently that I started wondering why. Why does the pitch go up in exceptional cases while it usually goes down? Pitch flattening may be okay because the resonator looks extended due to cross-fingering if the open hole in between is overlooked. This idea can be justified by a more sophisticated theory called lattice tone hole theory that was proposed by Arthur Benaid, a famous American musical acoustician, many years ago. On the other hand, it was puzzled why the pitch is occasionally raised. In the literature, it is explained so because the open hole works as a resistor hole. I am not convinced with this explanation. Opening the resistor hole or thumb hole results in a pitch an octave higher or more, not just a whole tone or semitone higher. Moreover, it is unsatisfactory to explain the same pitch bending phenomena with two different theories, depending on the pitch going up and down. These should be explained in a unified manner. I'm sure the physicists exploring the beauty of the nature agree on this point. So in this study, I proposed a simple model of two coupled mechanical oscillators for a unified explanation. The key idea is avoided crossing or level repulsion in quantum physics. Don't be discouraged even if you do not know these words. I will explain them in this video soon. Here is the model. The resonator of the woodwind instrument or a pipe is divided into two sections, above and below the open hole. Each section, upper or lower bore, works as a resonator and is represented with a spring mass system having constant K and mass m. The air in the open hole works as another mass vibrating perpendicularly to the pipe. These three masses are connected with lubricant oil. If you play the instrument with normal fingering, then the lower bore should have a frequency much higher than the upper bore. You see, the lower bore has many open holes lined up at short intervals. This makes the resonance frequency much higher. The model vibrates like this. Only the upper bore vibrates. The frequency is square root k over m plus capital M because two masses are vibrating jointly. I will call this omega u or upper bore resonant frequency. What happens if you close some holes on the lower bore? Its resonant frequency is gradually decreased and become comparable to that of the upper bore. Then these two bores start interacting by competing to capture the tone hole mass. As a result, this model vibrates at two different frequencies. One is lower and one is higher than omega u. Here is the animation of the model vibrating at the lower frequency. These two bores are vibrating symmetrically in this case. The tone hole mass vibrates 2 times faster than small m. Therefore, the model vibrates at square root k over m plus 2m, 2 times capital M, which is lower than omega u. This corresponds to pitch flattening or usual effect of cross-fingering. Here is the animation of higher frequency mode corresponding to pitch sharpening or anomalous effect of cross-fingering. This time, two bores are vibrating asymmetrically. Both of them fail to capture the tone hole mass and it stays still. The vibrating frequency is then square root k over m, which is higher than omega u. Here is the plot of two resonant frequencies, omega minus and omega plus. These are functions of omega L, lower bore resonant frequency. If omega L is sufficiently higher, omega minus is very close to upper bore resonant frequency. This is the pitch gained with normal fingering. When omega L is decreased by closing some holes and become comparable to upper bore resonant frequency, then omega minus is significantly lowered. This is pitch flattening. However, if omega L is further decreased, it becomes possible to excite higher frequency mode omega plus. This is pitch sharpening. Because two resonance frequency curves deviate from each other, this is called avoided crossing. You may have seen similar pictures in other fields of physics. So far, I'm sure the basic mechanism of pitch bending phenomena due to cross-fingering has been clarified. I will then explain the actual pitches played on the recorder. To do that, we need an extended model having 3 degrees of freedom. This time, upper bore has 2 resonant frequencies, omega u1 and omega u2. These are just the 2 lowest resonance frequencies. The lower bore is okay to have just 1 resonant frequency, omega L, as before. Here is a plot of 3 resonance frequencies. We have 3 because the model now has 3 degrees of freedom. You see the avoided crossing happened twice near the first and second resonant frequency of the upper bore. On this plot, I will overlay the actual pitches played on the recorder. These 4 notes are played with normal fingerings D6 and 3 cross fingerings C#6, E6, and D#6. In this order, more holes are closed and the resonance frequency of the lower bore is decreased. As these pitches are nearly on the resonance frequency curves, we can say that the simple model can explain pitch bending due to cross fingering as well as the pitch gained with normal fingering. Interestingly, if you change blowing pressure, we get more pitches. These are shown with note in parentheses. I will then demonstrate this note on each mode. First, mode 2. On mode 1. On mode 3, from D#6. I will then demonstrate pitches possible to play on each fingering. First, D6. C#6. E6. D#6. More interestingly, you cannot play F6 just after C#6 even if you increase blowing pressure. I will demonstrate what happens if you increase the blowing pressure on C#6. However, you can excite F6 just after E6. This is called hysteresis. However, it cannot be explained within the scope of the topic presented today. To study hysteresis, we have to consider the interaction between the air jet vibration at the mouth of the instrument and acoustic excitation in the pipe. I will summarize the presentation. Pitch bending due to cross fingering, both flattening and sharpening, can be understood with a model of two coupled mechanical oscillators. The mechanism is avoided crossing, which is a kind of universal phenomena often seen in many other fields of physics. In musical acoustics, it is known that piano tones decay in two steps. They first suddenly decay, but they later sustain. This is also explained with avoided crossing. In this case, two or more strings tuned in unison interacting with each other. Actual pitches of recorded cross-fingering were explained with an extended model with 3 degrees of freedom. At the end, I will give 2 references. One is the original paper in AST, the English Journal of Acoustic Society of Japan. This is for those who wanted to know more about the topic presented today. The second one is a short introductory article in Physics Today. It was my great pleasure that my research was covered by the editor of this journal. Thanks for watching. See you next time.